Okay, let's go ahead and get started. So welcome to our final STEM Friday session. We're so excited to have you here. And let's go over the agenda for today before we start. So we're going to start off with some creations from last week. Then we're going to talk a little bit about heat and energy. And then we're going to have our activity of the week, which is a solar oven. And then after that, we're going to have two speakers, Ms. Sandra Brindis and Mr. Gil Shoaf. And then we're going to go over some student highlights where we can show off the work that you guys have made over the past 5 weeks, which is really awesome. And then we will close it out. So to start, let's look at some of the creations from last week. So just as a reminder, last week you guys were challenged to make balloon cars. And I think this was one of the hardest challenges that we've had so far. So it's really amazing that some of you were able to make it. And these are just 2 that I picked out that were really good. The first one was from Yilong, and looks like he used some wooden wheels, and he made his body out of cardboard, and he even put some glitter on there, which is awesome. And then we had one from Rosabella, and she actually had a video, so we can watch the car go with the balloon on it. So that's awesome. Up next, we're going to talk a little bit about heat and energy. Someone said heat is a type of energy.
Yeah. All right, yeah, you're right about that. All right, can we go to the next slide? All right, so heat is the result of the movement of tiny molecules called atoms. This energy can be transferred from one object to another, which is called heat transfer. There are 3 ways that heat can be transferred, and those are conduction, convection, and radiation. Conduction is when thermal energy is transferred through touch and between any 2 solid objects. An example of this would be cooking food. When the pan with the food touches the stove, the heat will be transferred from the stove to the pan. The next example is convection. Convection is when thermal energy is transferred through fluids like a liquid or a gas. Only one of the objects has to be fluid for it to be convection, though. An example of this would be boiling water. As the pot gets hot, the heat is transferred to the water.
All right, so what is radiation? Radiation is the effect of heat transferred through infrared energy. Infrared energy is a form of radiation made up of fast electromagnetic waves. An example of this is the sun. All of the light, heat, and UV light that we get from the Earth comes from the sun. These 3 types of energy are radiated throughout our planet because the sun is very hot. Other types of these electromagnetic waves are microwaves, radio waves, X-rays, and gamma rays. Can we go to the next slide? Okay, so thermal conductivity is the ability for an object to transfer thermal energy. For example, certain objects are good at conducting heat, like metal and glass, but other things are bad at conducting heat, like air or wood. An example of a household object that uses conductivity is a thermos. Thermos has a very low thermal conductivity to keep your food hot. Heat can't transfer through the thermos and stays inside the thermos. That's why the food stays hot. While thermal energy and temperature correlate, meaning that when temperature increases, the thermal energy also increases, they're not the same. While temperature measures how hot something is, heat measures the amount of energy that something has. So when an object's thermal energy changes by conduction, convection, or radiation, its temperature will also change because of this correlation.
So for our last STEM Friday challenge, it's the solar oven. First, let's talk about what a solar oven is. A solar oven is a device that lets you cook food without using any electricity and without burning any fuels. The oven heats up just by using the heat from our sun. Here's some materials you might want to have for building your solar oven. You want to have some form of cardboard box, which can be a pizza box, delivery box, or just any type of cardboard box works. clear plastic sheets or plastic wrap, tape, or any other adhesive, and some aluminum foil. Start off with building your solar oven. Pick your cardboard box and try to seal all of its sides and edges using tape. It's a good idea to do this as a measure to prevent convection, which, if you recall, is the transfer of heat and fluids from happening between the inside and outside of the box. Our next step is to cut a hole in the top of your box. Make sure to keep the excess cardboard. You want to attach a piece of aluminum foil on for the next step. Then put that piece of cardboard with your aluminum foil sides towards the box onto one of the edges of your cardboard box. So this part acts kind of like a funnel, catching more sunlight and focusing more energy into your box when you put it outside. For your last step, seal up the hole in your box with your clear sheet or plastic wrap. To make your oven work the best, there's two main things that you'll have to do. First is to increase the thermal energy or heat that goes into your oven. Having a bigger box or reflector is going to help you. Bigger box or reflector means more surface area that the sun can enter your oven through. However, you also have to be careful with this.
Where are you going?
Sorry about that. You also have to be careful with this because this also means that heat has more ways to easily go out of the oven, whether it's through convection or conduction. You also want to tweak the angle of the sunlight going into your oven. You want direct sunlight because it means that the energy going into your oven is going to be the most powerful. As the day goes on, where the sun is in relation to your oven is also going to change because the earth is rotating. Next thing you can do is to decrease the amount of thermal energy or heat going out of your solar oven. There's always going to be heat energy leaking out of your oven because of the second law of thermodynamics. That means that heat wants and mostly always will flow from hot to cold. You can try to minimize this by taking measures to insulate your box. Some ways you can do this is by layering on an extra sheet of cardboard to the sides of your box, or by constructing a windshield using some more cardboard to prevent wind from cooling down your oven. A way that you can tell if your oven is well insulated is by touching the sides of your oven when there's no wind. The cooler the outside of the box feels, more heat's going to stay inside of your oven. By doing this, you'll be measuring the thermal conductivity of your oven, which you want to be as low as possible. And the last thing, one of the most easy ways that heat can escape your oven is through hot air inside your oven exchanging with cooler outside. Just double check that your oven is sealed really well. Here's a few more things about your solar oven. Try to have an adult help you if you're cooking something inside of your oven. The sun's very powerful, so your oven can get really hot. Your solar oven will work the best on sunny days, so try to check the weather in order to get as much sunlight as you can. This week, the best times to test out your solar oven will be from Tuesday to Friday next week. So that'll be the 26th to the 29th. And one last thing, when you're cooking something in your oven, you'll probably have to change the cooking times in the solar oven when compared to your kitchen appliances. Check with an adult, make sure the food in your oven is fully cooked. Here's some example pictures of solar ovens. And just a few extra things. Make sure to email any questions as well as your solar oven submissions to stemfridays@gmail.com. Just a reminder, students who have participated in these STEM Fridays so far will be getting tickets to Cortechs STEM fairs, our Build Space tours, and FLL camp.
Awesome, thank you, Eric. So this week we actually have two very special speakers. If you guys were here the first week, you remember that the speaker was from our own team, so we thought it would be cool if we also ended it with speakers from our team. So our first speaker is Ms. Sandra Brindis, and she's actually the coach of our team and founded our team about 6 whole years ago. And at the beginning, we didn't have a build space or anything. And if you guys remember the big robot that we built, we actually used to build that out of her garage, which is crazy. And she's an integral part of our team, and she's going to share a little bit about the clinical trials process, which is really relevant as right now with coronavirus, they're trying to do the same exact thing to find a vaccine. So Ms. Brindis, take it away.
Hi, thank you for that nice introduction. I'm pretty excited to talk to you about something that is relevant and current today. So a little background on myself. Shreya said I was the coach, but before I got involved in robotics, which is very exciting. It's a field I never thought I would be involved in. I worked at Pfizer conducting clinical trials. So if you have your TV on during the day, I'm sure that you are listening about the race to get a vaccine or a medicine or drug that will help us with the coronavirus. And I thought I would give you a little background about what it takes for medicine and a vaccine to get from the point in the lab all the way so that it's safe and effective for us to use. I got involved in clinical trials. I studied psychology in college, and I learned how to design experiments and to think about problems and how we go about solving them. I also took many classes in biology, chemistry, and biochemistry that helped me when I was offered a job to do clinical trials. Next slide, please. So let's think about it. We know that there's the COVID-19, which is a disease right now all over the world that we're looking to find medicine or vaccine to cure. In the chat, are there any diseases or illnesses that you think we should find a cure for? In the past, young children in the 50s would have polio, and they developed a vaccine for that. We have vaccines for chicken pox and mumps. Cancer, that's a great one. And I can tell you that right now, there are a lot of clinical trials that are looking at a cure for cancer. SARS, that's another one. That's very good. Cancer is a big one. Cancer in children, cancers in adults. Oh, appendicitis. Somebody must have had appendicitis. Heart disease, very good. There are some drugs already on the market that help with heart disease, but companies are always trying to get better drugs that are safer and even more effective. Cholera? Yeah, I don't think we have medicine for cholera. You're right. That's an old disease. That's great. Now, some of the terms, I want to help you understand some of the terms that you might be listening on TV. Clinical trials and the FDA. So before anything goes into this general population, it has to be approved by the FDA. And the FDA stands for the Food and Drug Administration. And that's very good. So let's go to the next slide, and we'll get an idea of what it takes for a drug, vaccine, also devices. So pacemakers, a lot of the biomedical engineering devices have to be approved by the FDA. But before it even gets to that point, that the FDA looks at the data to approve, there are 4 phases. This slide shows 3 phases. I'll tell you about the 4th phase. So it starts in a lab, and it takes a lot of trials and tribulations and failures to even come up with one medicine or drug that scientists think maybe might work. So if they find something that might work, they start to study the medicine or the drug with animals. And yes, they use mice, then they use beagle dogs, and they want to make sure that it's safe in animals. If it passes that test, it goes to the first human trial, phase 0. And that's the first study in a patient to see how the body metabolizes the drug, or how does the drug that was now used with animals, how is it working with people. Phase 1, in that phase, the most important thing for a drug, the first thing that scientists have to prove is this drug or medicine safe? It has to be safe. That's the most important thing, because you don't want to develop a drug that will cause more harm than the disease itself. And in that first phase, they're trying to figure out what dosing they're going to use. And the rule of thumb is try to get the smallest dose that's going to be the most effective. The second phase, you start to include more people, and these are clinical trials. You're still looking at safety. Now you're getting a lot of people. You want to make sure you get as many people trying this drug to make sure it's safe. If it passes the safety test, it goes into phase 3, and these are big trials, which means there's a lot of centers across the country, across the world, where you have people participating in clinical trials. At this point, at phase 3, you're not looking just at whether it's safe, you're looking as to whether it's effective, right? And everybody knows what effective means. I see here phase 0. I think I don't think it's just one patient. I've never seen that phase 0. I find that kind of interesting. Usually we go right into phase 1. Okay, so now we have a lot of data. And let's go to the next slide. What happens in a clinical trial? How do we collect these data? So there'll be different, we call them investigator sites, and they'll put word out that they're looking for people that are interested in participating in a clinical trial. So you would go into the doctor's office, and they're going to collect information about you and give you information about the trial. Then you have to sign an informed consent form. Do you know what an informed consent form is? Let's see, let's put it in the chat. This is very important. No one can participate in a clinical trial without an informed consent form. Anybody? An informed consent form tells you, the patient or the subject, everything about the study. And when you sign it, it means you're going to participate in the study, and at any point you can leave the study. Oh, yes, okay, the patient was, okay. Once you sign the consent form, then you become part of the study. They're going to screen you. Every clinical trial has a protocol, which means what patients can be included, what patients can't be excluded, what patients should be excluded. Can you think about a type of patient that should be excluded in a clinical trial? How about women that they're called childbearing, which means they can have babies. So you don't want to have women that can have babies participate in clinical trials, because remember, this is still experimental. So once you decide if you're accepted into the trial, you've met all the requirements, you'll have your first baseline visit. And that's to ensure where you're at before you're given the medicine. Next slide. Now, at that point, you're randomly assigned, which means you have some patients that go into the group that gets the medicine, the study drug. You have some patient that goes into the group that gets a placebo. And a placebo is you're taking a pill, but it's like a sugar pill. And that's the control group. So by the end, they can compare those that took the medicine to those that took a sugar pill to see if there was a difference. Then you go along, you follow the procedures, you go to the clinic or the doctor's office, depending on the study, every week, every other day. And then they'll do evaluations, and they collect data on every patient that's in the study. And they look at safety, and they find to see if it's effective. Next slide. So that's a clinical trial. So it takes a long time from the point that it starts in a test tube in a lab all the way to phase 3, where you're collecting all this information. So all this information is then submitted to the FDA, and they decide whether that vaccine, that drug, that device can now go into the public. So when you go to the doctor's office and they give you an antibiotic or something to make you feel better because you're not feeling well, you know that that medicine or drug has gone through a very rigorous and long process to get it to that point. So what does this have to do with STEM? Well, if you're interested in helping to find cures and drugs to help in illness and vaccines and devices, you can go into becoming biologist, biochemist. You can be statisticians. You have to look at the data to make sure if this drug really worked and it's safe. Here's a question. What other ways would you use STEM skills to conduct clinical trials? Have you thought about becoming a biologist or a chemist or a statistician? Anyone? That's great. It's really exciting, and you would be involved in work that can really make a difference. Does anybody have any questions? So right now, what's going on, Pfizer actually has a vaccine. They're working with another company to find a vaccine, and the reason why it's been accelerated, the medicine the vaccine that they were looking at, I believe they were looking at it for SARS. So they did a lot of the safety, they collected a lot of the safety data. The process can take a long time, from the time it goes from the lab all the way to a phase 3. It could take years. Because, and it depends on the drug, and it depends how long it takes for recruitment. Because when these studies are run, you have to recruit patients to the study. And it depends on how quickly you can recruit patients. That's a great question. Any other questions? Well, thank you. If you guys have any questions after this is over, please email us and I'd be happy to answer them.
Awesome. Thank you so much, Ms. Brindis. Next up, we have Mr. Gil Shoaf, and he's been mentoring our team and inspiring us for about 4 years now, and he's our lead engineering mentor. So that being said, he's going to talk to you a little bit about engineering and the incredible things that he creates as an engineer.
Hey everyone, thanks Shreya. Like she said, my name is Gil Shoaf. I currently work as what's called a product engineer for John Deere. I went to school here at NC State, so go Wolfpack. And I just want to talk to you guys today a little bit about kind of what engineering is, what I do, and maybe what you can do with some STEM skills that you've been learning throughout these last few weeks. Slide, Shreya. So what is engineering? When you guys think of engineering, what do you guys think engineers do? What do you think they can work on? What do you guys think? You can unmute your mics or type in the chat box. Exactly. Engineering is basically problem solving. It's just a fancy word for problem solving. Building this, yeah, engineers build things. Design, test, build, that's really good. I'll actually get into that just a little bit later. Yeah, so if you look at the pictures on the slide, there's a bunch of different types of engineering. If you look in the top left, you can build big buildings, skyscrapers, bridges, roads, all sorts of things like that as what's called a civil engineer. In the middle, you can see a car. So that's what's called mechanical engineering, building machines and mechanical devices. You can build cars, different machines, work in factories, building machines that build machines, all sorts of stuff like that. Over in the top right, you can see an airplane. That would be what's called aerospace engineering. So you can work on airplanes, spaceships, rocket ships, commercial airplanes, military airplanes, anything that flies in the sky, basically. You can do that as what's called an aerospace engineer. Over in the bottom left, kind of similar to what Ms. Brindis was talking about, you can become a chemical engineer. So with that, you can use different chemical compounds and solve all sorts of problems, whether it be creating different coatings to put on different things, making cleaning supplies, all sorts of different things. There in the middle, you guys can see a bunch of different robots that look kind of cool. That takes kind of a bunch of different types of engineering, but there's what's called electrical engineering. So electrical engineers work with electronics, wires, and circuit boards, and all sorts of stuff to build their solutions. And then in the bottom right, you can see a guy that's missing a leg and is getting a prosthetic leg. So there are what's called biomedical engineers that create engineering solutions for the medical field, whether that be prosthetic limbs, medical equipment, testing equipment, like X-ray machines, MRI machines, anything in the health field you can do as a biomedical engineer. So what about John Deere? What do you guys know about John Deere? What do they make? What do you think when you hear about John Deere? Yeah, they make equipment. Do you know what types of equipment they make? Yep, for farms. Tractors. Yeah, that's what we're pretty famous for, right? John Deere makes tractors. Oh, yep, exactly. Stuff for building. So we also make construction equipment. Those are kind of the two main things that John Deere makes. We make things for farmers. We make things for construction companies for building roads and buildings, all sorts of big machinery. We also do a lot of other cool things. Yep, we dig in some sand. I actually work in a smaller group for John Deere that works on golf equipment. Yep, we make lots of lawnmowers as well. So I actually work on a special type of lawnmower, as you see right there in the bottom. This is a machine that I work on every day. It's designed to mow golf courses. So if anyone's ever been on a golf course, this machine is specifically designed to mow the green, which has the hole in it where you're trying to get the ball. So as a part of all of these machines, you've got all sorts of different types of engineers working together to solve a problem. Tractors solve a problem by doing heavy lifting and pulling heavy equipment to be able to plant in fields. Construction equipment solves problems by moving dirt, lifting heavy things, moving things around. And lawnmowers and golf equipment solve problems by maintaining grass, making sure you can go play in your yard and people can play golf, things like that. So all of these different products require mechanical engineers to design the structures, you know, the metal and the tires and the hydraulics and things like that. They take electrical engineers to design all the lights and the computers and all the electronics on the machines. Modern tractors actually are some of the most highly advanced electronic machines made in America, actually. That tractor on the left there will actually drive a perfectly straight line all by itself without an operator. And then when it gets to the end of the field when it's time to turn around and come back, it will do that all by itself. And the person driving the tractor just has to kind of sit back and relax and make sure nothing goes wrong. So in product engineering, it's kind of a combination of all sorts of different types of engineering to come up with a problem solution. So as a product engineer, there's kind of a few steps you generally go through. The first step is basically designing your solution, coming up with the idea. In today's world, usually that means you're doing it virtually. So this picture shows a picture of what's called a CAD model. Does anyone know what CAD is? Great. Can you describe what it is? Computer aided design. Yeah, that's really good. So what CAD is just an acronym for computer aided design or computer aided drafting. It's basically, this picture here shows a picture of a drill, and all those parts are made on a computer. It's kind of like a super fancy version of like Minecraft, where you take on your computer, you can build anything you want. So that's kind of the first step. You get your ideas, you make your virtual design, and then what do you need to do after that? Build, exactly. So once you have your design, you need to build it. So during product engineering, you think up your design, you do the best you can, and then you build it. You make a prototype. So this just shows a picture of a guy welding some metal together. You can build in lots of different ways. You can use bolts and screws, you can use glue, you can use cardboard and wood with some balloons, like you guys made your balloon cars last week. You can use cardboard, saran wrap, and tape to make ovens. Any sort of material. You have your design, and then you just build it. So after you build it, what do you think is important to do after that? You've got your design, you've got it made. Now what do you do? Test it, exactly. So this picture shows a picture of a test. So this is a picture of a crash test, which is used by different car companies, where they have the design of their car, they make the car, and they want to make sure it's safe for everyone. So they do this crash test to make sure that if a person got in a crash in this car, that they would be okay. Testing involves a lot of different things. You want to test and make sure your design works like you thought it would. You want to test and make sure your design doesn't break if somebody uses it incorrectly. Basically, you just take your design and you try it out. You try it out in a whole bunch of different ways. So what do you guys think would happen if you if you came up with your design, you built it and you tested it, but it didn't quite work right? Yeah, exactly. You guys kind of beat me to it already. You fix it, right? If you test something and it doesn't work, you basically loop back to the beginning, change your design, build it, and test it again. Let's show you if you go to the next slide. So that's what's called the engineering design cycle. So if you look, this is kind of what we just talked about, right? You start with your design, you build it, you test it, and then you learn from it. And then you redesign, you build it, you test it, and you learn from your test. And you just keep going in a circle until you have a product that you're happy with. So how can you use this design cycle or engineering in your life? What are different things you can design or different ways you can use this idea? Experiments. Yep, you can design different experiments or do things with school, things like that. How about your STEM Friday activities? That kind of is using design and engineering, right? Yep, cooking. You can try to make different cooking. I think your STEM Friday activities are a great example. Last week with your balloon car, did the first thought you thought of actually work when you went to build it? Or did you kind of have to try something and then change a little bit and try it again? So two things that I think you guys would definitely be able to use this process with would be something like Minecraft and Legos. How many of you guys know what Minecraft and Legos are? Or how many of you guys like playing Minecraft or playing with Legos? That's what I thought. So you can use these processes when you're designing your Minecraft houses, or you're trying to build a cool little machine to do something. You think about what you want it to do, you build it, you try, and then you try it out. And if it doesn't work, you change your design, you try it again. Same thing with Legos. If you want to build a cool little tractor, you think about it, you build it, and if you don't like something, you just circle back and try it again. Anything you guys do, you can use this design process to help with that. Any problem you have, anything you're trying to build, you can use this design process. That's about all I have. Do you guys have any questions?
So next, we're just going to go through some of your creations that you guys have been making throughout the last 5 weeks, and they're really cool. So let's take a look at them. So the first couple are by Elon. He made a mask, he made a parachute, and he made a really, really cool Rube Goldberg machine. So good job, Elon. Next, we have Rosabella. She made 2 parachutes, a really cool Rube Goldberg machine, and she also made hand sanitizer. Next up, we have Blake, and he also made a Rube Goldberg machine, which looks really intricate with his pump and the dominoes and the string, and he also made a really cool mask. Next up, we have Avery, and he made a really cool Rube Goldberg machine. Next up, we have Ella. She made a parachute and a Rube Goldberg machine, and it has a lot of cool like slides and twists and mazes, which is really awesome. We also have Samhita, who made hand sanitizer, and we have Vaibhav, who made a Rube Goldberg machine, and it actually shot that arrow and popped the balloon that the bear is holding. So that was really, really cool. And we have Ethan, who made a Rube Goldberg machine, and he made a parachute. And we have Simran, who also made a Rube Goldberg machine, and we have Jaden, who made a mask. And we have Oddvik, who made a mask, 2 different masks, and he made a parachute. So for all you students who submitted your stuff, we'll be sending you certificates in the mail. So congratulations, your stuff was really, really cool, and we loved seeing what else you have to make. And if you guys still want to participate, if you guys send in your creations from this week, your solar oven, we'll still send you a certificate, and we can display your creations, and we'll send it out to the rest of your peers. So these are just some reminders before you guys leave. So I just talked about the certificates, and the next thing is the post-program survey. So after the session, we'll send you or your parents a really short survey, and we just wanted to see if you enjoyed the sessions, what you wanted more of, what you wanted less of. So next time we do one of these kinds of programs, we can make it even more, even better, and even more enjoyable, so that you can learn from it and have fun at the same time. And the next one is that Cortechs has a lot of mentoring programs. So we'll contact your parents through that too. And if you guys are interested in joining an FLL team, which we talked about on the first week, or a junior FLL team, you can email your name to us, and we would love to form teams and mentor. And also, I know a lot of you already are on junior FLL teams, and if you guys need help throughout the season, or if you guys just wanted to show off your work to us, we would love to have you come in once all of this once the coronavirus kind of calms down, and we would love meeting you then. And lastly, thank you guys for coming every Friday and spending your time. We've had an amazing time with you, and we hope you learned something out of this. You can always contact us at Cortechs Robotics if you have any questions, or want to be involved in some of our other programs. So that's pretty much it from us. And just remember that this learning doesn't end here, so you can keep creating, experimenting, picking things apart, and learning how they work. And if you guys build anything over the summer, definitely shoot us an email, and we'd love to see what you make. So thank you all, and this is pretty much it for STEM Fridays, and we'll stick around for questions. But other than that, enjoy the rest of your day and stay safe.